This video is on doing integration using the substitution rule. So we're going to lay out a few basic rules and then we will do several examples to help us. The substitution rule helps us to undo things that were complicated derivatives. So if we had to do a multiple chain rule type of thing, then we would have to look at doing the substitution rule. So the first thing I want to do is help us with a few steps. The first step is to substitute f for a function within your integral. Now, how do we know what to make f? We make f things that look like a bunch of stuff to a power, or the square root of some stuff, or a exponential where we have base a to a bunch of stuff, or we might have 1 over a bunch of stuff. So what we're looking at is when we have a function that has a mini function within, then that we want that stuff to become our f. Now, what we have to then do is create an integral that is the function f and then df. So we have to make sure that we provide for that df. This is where we are undoing the chain rule where you kept multiplying by pieces because of the chain rule. This is making sure that we acknowledge that. So we may need to adjust our df. And I'll show you what we mean by that in a minute. Okay. Then we integrate, and then we substitute back in for f. Alright, so let's try an example with this one. If we had the integral of 4 2x plus 5 to the third dx. We could try other methods, and it's possible that you can use other methods, but the substitution is going to help us anytime we have many functions within. So I have this function right here that is inside of all that other. That is what we're going to let f be. F is going to be 2x plus 5. So when I rewrite this integral, I'm going to put the 4 out front. I'm going to put the 2x plus 5 is going to become f to the third. And then I have to make sure that I represent df. And df, the derivative of f, is 2 times the derivative of x, which is dx. I have a dx right here, but I don't have the 2 that I need to have df. So what I want to be able to do is I want to be able to write df right here. But I can't write df if I don't have a 2 dx. And all I have is a dx. So let me kind of recap everything. This 4 is that 4. I haven't changed anything. 2x plus 5 is the same as f. I haven't changed anything. My power of 3 is still my power of 3. But my dx, in order to become df, has to have a 2 with it. So we can put a 2. But now I have multiplied this function by 2, or this integral by 2, to balance that out. To balance that out, I have to multiply it out front by 1/2, because 1/2 times 2 is really just 1. So I'm just changing how it looks. So 2 dx matches df. And so now if I bring this 1/2 down, so 1/2 times that 4, I can have just my df there. So what I really have is 1/2 times 4 is 2 times the integral of f cubed df. This part right here with the star is the most critical part. That to replace dx with df, you have to have everything that df equals. Now we can integrate this, and so when we integrate, remember we increase our power. So this would be 2, increase our power by 1, divide by the increase. 2 over 4 becomes 1/2, f to the 4th. And now, in place of f, I'm going to put back what it equals, 2x plus 5 to the 4th. And now I can add my plus c. Let's try another example. The integral of 9z square root of 3z squared minus 7 dz. Now the reason we would look at this and know that we have to do substitution is that we have two variables, a z here and a z here, and there's no way to clean that up by multiplying in by the 9z. So I'm going to pick the big function. You want to get rid of the most complicated function, most likely. It's going to be inside a square root or raised to a power. And so we're going to call f 3z squared minus 7. So we need to know what df is, which is 6z dz. So let me rewrite a few things and watch what I do. I always get in the habit of putting the coefficients just out front. I need this z to go with this dz because I have a z dz that I need to worry about. So I'm going to bring that down here and put it with the dz, and then I'm going to have the square root of 3z squared minus 7, which we called f. Now I have almost everything I need, but in this green box I have 6z dz. I only have a z dz, so I have to put a 6 right here so that this matches. But if I put a 6 there, I have to multiply by 1/6 in the front. And so now we're ready to do the substitution. 9 times 1/6 is 3/2. The integral of the square root of f, and now that green box becomes df. So we do 3/2 integral of f to the 1/2 df, which is 3/2 f to the 3/2 divided by 3/2, which becomes f to the 3/2, and we're ready to plug in for f, so that would be 3z squared minus 7 to the 3/2 plus c. So we plug that back in. If you're bothered by that df and what happened to the 6z, is take the derivative of that answer and you're going to see that times 6z show up, and basically what we're doing is undoing that by having it sucked back into the problem when you do the integration. Let's do another example, and that is the integral of e to the x over e to the x plus e dx. Now we can integrate just e to the x. The problem is this is really e to the x times e to the x plus e to the negative 1 dx. We cannot distribute the e to the x here, and so now we technically have two variables. We have this e to the x and this e to the x, but the second one is part of this whole binomial, so that's going to be our stuff. So our f is going to be e to the x plus e, and therefore our df, well, remember the derivative of e to the x is e to the x, so df equals e to the x, and the derivative of e, remember e is just a number, so the derivative of that is 0, so it's e to the x dx. If I bring this back here with dx, I would be able to say e to the x plus e to the negative 1 e to the x dx. What I have in the green box here, the derivative of my stuff, I have here. So I'm ready to call that df. So I have the integral of f to the negative 1 df. And the integral of f to the negative 1 is ln absolute value of f. And the reason you have to have the absolute values is because you can only take the ln of a positive number, and we don't know what f is, whether it's positive or negative. You don't really need it here, but we typically leave it because e to the x plus e is going to be positive no matter what. And one more example. Let's go with something that looks like this. And then the question is, which one do we make our f? You want to pick the one that is most complicated, because remember, when we take the derivative of it, we're going to probably need the pieces below it. So 3x minus 9x squared is our most complicated. So we're going to make f be 3x minus 9x squared. So df equals 3 minus 18x. Okay, and so we need to make, and then we times dx, because we always have to have our dx. So if I rearrange this, I'm going to have this up in the power, and I've got 1 minus 6x dx, but my two boxes don't match. But it's close. If I multiply the 1 minus 6x times 3, I'll get the 3 minus 18x. So I would need to multiply by 1/3 out front. And so I'm really integrating e to the f df. And the integral of e to the f is e to the f, which is 1/3 e to the 3x minus 9x squared plus c. And so again, the purpose of substitution is to get the most complicated stuff out of your problem, and then by doing that you are able to integrate as long as the df is can be represented. If there was not a df, for example in this last problem, if we did not have the 1 minus 6x, then you could not integrate this using one of the methods we know. You would have to go and get that integral book out and see if you could find a match in order to integrate this some other way, meaning that it's a function that's been merged together kind of thing. So make sure, the key is making sure that your DF is represented even if you have to adjust things. So keep practicing and definitely practice substitution. And the hardest part is identifying what to make F, and then from there I think it rolls a little bit. So good luck with your work on integrating.